All right, this is the second section of the intermolecular forces. This section, we're going to look at the vapor pressure and do some calculations. Please pay attention to each step. You can pause the video, and then when we get to the interactive section, you have to be completing the boxes before I move forward so that you know that you know what you are doing. Okay.
Consider a liquid placed in a closed container. Initially, molecules are transferred from the liquid to the vapor phase. This process is called evaporation. Initially, as the number of vapor molecules increases, so does the rate of return of these molecules. This process is called condensation. Eventually, the rate of evaporation equals the rate of condensation. At this point, the system is at equilibrium, and no further changes occur in the amount of liquid or vapor. The equilibrium is expressed as the vapor, like any gas, can be assumed to obey the ideal gas law. Once the system reaches equilibrium, the pressure exerted by the vapor is called the vapor pressure. As long as both liquid and vapor are present in the container, the pressure exerted by the vapor on the liquid is independent of the volume of the container. The vapor pressures of liquids vary. Liquids with large vapor pressures are called volatile liquids. Volatile liquids evaporate rapidly from an open container. The vapor pressure of a liquid is determined by the strength of the intermolecular forces in the liquid. In general, liquids with large molar masses have relatively low vapor pressures. This is because molecules with large molar masses have greater London dispersion forces.
I want you to take note of all these words, this particular information. In general, with large molar mass, liquids with large molar mass have relatively low pressure. All right, look at that. And then this because molecules with large molar masses have greater LDF. LDF means London dispersion forces.
Molecules with hydrogen bond have low vapor pressure compared to molecules of similar molar masses that do not have hydrogen bond.
That's a very important aspect for you to remember. Even though the molar mass might be higher in other compounds, you're going to see an example later. But the one that has hydrogen bond will be the one that will have the higher boiling points. And of course, with low pressure. Low pressure means higher boiling point. So remember, hydrogen bond is between hydrogen and fluorine, hydrogen and nitrogen, hydrogen and oxygen of different compounds or different molecules, not on the same compound, all right? So this is not to say that HF has hydrogen bond. No, this is to say if you have two different HF like this, so this bond between the fluorine on one molecule of hydrogen fluoride or one molecule on a compound of hydrogen fluoride with another hydrogen on the other compound. That is when you have hydrogen bond, not the bond within them. Of course, remember this is your intermolecular forces. So you're talking about intermolecular forces right now, not intra. This is intra. We are not referring to intra at all. We're looking at intermolecular forces because all these examples relate to intermolecular forces.
Example: the vapor pressure of a liquid is 115 millimeters mercury at 38.9 degrees Celsius. If the heat of vaporization of that liquid is 40.5 kilojoules per mole, calculate the final temperature in degrees Celsius when the vapor pressure is 760 millimeters mercury.
And this is a worked example. This is a guided example. Please follow the example step by step. You have units you have to pay attention to, and also the values.
P1 in millimeters mercury equals
Okay, let me move back a little bit before we go to the calculation. I want to talk a little bit on the vapor pressure.
the plot between vapor pressure and temperature for water is. This is a curve. The temperature on the x-axis is in degrees Celsius. The vapor pressure P on the y-axis is in millimeters mercury. In order to obtain a straight line, we must plot the natural log of P versus 1 over T. Note the temperature is in Kelvin, K. Often the numbers on the plot are shown as, and the x-axis is labeled as. This means that the number on the x-axis is 2.5 times 10 to the minus third power, and so on. The straight line gives a negative slope equaling negative delta H vaporization divided by R. The general equation for the straight line is y equals mx plus b, or the natural log of P equals minus delta H vaporization divided by RT plus B. For a given liquid, if P1 and T1 are the initial pressure and temperature, and P2 and T2 are the final pressure and temperature, then the natural log of P1 equals minus delta H vaporization divided by RT1 plus B. The natural log of P2 equals minus delta H vaporization divided by RT2 plus B. Subtracting the two equations, we get the natural log of P2 minus the natural log of P1 equals minus delta H vaporization divided by RT2 minus the quantity of minus delta H vaporization divided by RT1. The natural log of P2 divided by P1 equals minus delta H vaporization divided by R times the quantity of 1 divided by T2 minus 1 divided by T1. Or the natural log of P2 divided by P1 equals delta H vaporization divided by R times the quantity of 1 divided by T1 minus 1 divided by T2. This equation is called the Clausius-Clapeyron equation. The Clausius-Clapeyron equation can be used to calculate any one of the following: P1, P2, delta H vaporization, T1 or T2. Note the value of R to be used here is R equals 8.31 joules per mole Kelvin. Example: a liquid has a vapor pressure of 283 millimeters mercury at 50.00 degrees Celsius. If its heat of vaporization is 30.8 kilojoules per mole, calculate its vapor pressure in millimeters mercury at 25.00 degrees Celsius. Delta H vaporization equals 30.8 kilojoules per mole. Thus, convert delta H vaporization to joules per mole. Equals 30.8 times 10 to the third power joules per mole. P2 equals 283 millimeters mercury. P1 is to be calculated. T1 equals 25.00 degrees Celsius. Equals 298.15 Kelvin. T2 equals 50.00 degrees Celsius.
Right, remember, if you want to convert the temperature Celsius to Kelvin, you need to add 273.15 to the values of the Celsius. So 273.15 plus 25, which is the temperature given here, your vapor pressure in millimeter mercury at 225 degrees. So this will give us 298.15. And that is how we got this Kelvin. I'm going to do the same thing to the T2. All right, that means plus 50, 50 plus 273.15.
Equals 323.15 Kelvin. Rearrange this equation. Equals 0.963. The natural log of P1 equals equals 5.645 minus 0.963 equals 4.68. P1 equals e to the 4.68 equals 108 millimeters mercury.
Remember, if you want to use a calculator, you press your lane. It's in your scientific calculator. You see ln, press that, and then punch in the numbers that you desire. And then if you want to get your e, that is the antilog of that, you press the second function. If you're using scientific calculator TI30XS, you press your second function and then you press your E. Of course, it's going to be the lane, second function lane. At the top of that lane, you see the E exponents. That is how you get this E from second function lane. Then it will give you E exponent. Then you put in 4.68. And that will give you 108 millimeter of mercury. That is your P1. Now, interactive section.
Example: the vapor pressure of a liquid is 115 millimeters mercury at 38.9 degrees Celsius. If the heat of vaporization of that liquid is 40.5 kilojoules per mole, calculate the final temperature in degrees Celsius when the vapor pressure is 760 millimeters mercury. P1 in millimeters mercury equals.
Now you have to look at the values you're given in the question just to collect your data. What is the P1 in the question? Plug in the number there. So make sure you pause the video to figure out what is the P1 before you click continue. The P1 is 115 millimeter of mercury. That is the first pressure given. What is your P2? Your P2 is 760 millimeter of mercury. That is the second pressure. What is your T1? Get your calculator and get your T1. Remember, you have to convert the Celsius to Kelvin. And your T1 will be 38.9. Celsius in Kelvin will be 312.1. Your T2 is what you're looking for. So your heat of vaporization is what? In kilojoules per mole. Right, any question? and then your heat of vaporization in joules per mole, you have to convert it to joules per mole. That means you multiply by 1,000. So this is what you get once you do that conversion and you plug in the values. Now that formula, I think, is part of the AP formula sheet. It should be there. So you don't have to memorize the formula, so that you have to know how to use it. That is the only problem you have, how to use it. So make sure what do you get when you solve this? This very one will give you that. When you solve this, what does that give you? You get that. So when you solve this, what do you get? 1/3.312.1 will give you that. Raised to power 3, you know, it's supposed to be 0.0032 or 4 or something. All right, so when you solve this problem, this very particular side, you get what? Remember, it's like a fraction. Your denominator is k. You get that. So your T2 is going to be what? And that is T2 in Kelvin. What is a T2 in Celsius? What do you do? Once you get your Kelvin, what do you do to get your Celsius back? Subtract. That will give you 81.9 degrees Celsius.
Place a liquid in an open container and apply heat.
Right, we're going to the boiling point section of that. Let's see what we have here.
Initially, small bubbles form, usually at the bottom of the container. These small bubbles are air bubbles. Eventually, at a certain temperature, large bubbles form throughout the liquid. This is when we say the liquid begins to boil. The boiling point is defined as the temperature at which the vapor pressure of the liquid is equal to the pressure above its surface. Thus, the temperature at which the liquid boils depends on the pressure above it. In an open container, it is primarily the atmospheric pressure. The pressure inside the large bubble is due to the vapor pressure of the liquid. When the vapor pressure of the liquid becomes equal to the atmospheric pressure, the bubble rises to the top and bursts. The boiling point of a liquid is constant at a given pressure. At higher altitudes, where the pressure is low, the liquid boils at a lower temperature. The normal boiling point is defined as the temperature at which the liquid boils when the atmospheric pressure is 1 atmosphere. Liquids that have hydrogen bonds have higher boiling points compared to liquids of similar molar masses that do not have hydrogen bonds. Boiling points of polar molecules are greater than boiling points of nonpolar molecules of similar size. This is due to weak London dispersion forces in nonpolar molecules. In principle, there are two techniques to convert a gas into liquid. 1. Changing temperature. By cooling a gas, the kinetic energy of its molecules can be decreased. Eventually, the molecules aggregate to form small drops of liquid. 2. Changing pressure. By increasing pressure on a gas, the volume decreases. Hence, the average distance between the molecules decreases. As the molecules approach each other, they start to feel the weak intermolecular attractive forces. Industrial gases are liquefied by the combination of these two techniques. In every substance, there is a temperature above which the liquid phase of a pure substance cannot exist, no matter how much pressure is applied. This is called the critical temperature. The critical temperature is expressed as capital T, small subscript c. In every substance, there is a minimum pressure that must be applied to liquefy that substance at T sub c. This is called the critical pressure. The critical pressure is expressed as capital P subscript c. Cooling a liquid transforms it into a solid. This is called freezing. Conversely, heating a solid transforms it into a liquid. This is called melting or fusion. The melting point of a solid or the freezing point of a liquid is defined as the temperature at which the solid and liquid phases coexist in equilibrium. The normal melting point or the normal freezing point is defined as the temperature at which the substance melts or freezes at a pressure of 1 atmosphere. Consider the heating curve of a substance. The heating curve is a plot of temperature versus time. When a solid is heated, its temperature increases gradually up to point A. At point A, the solid begins to melt. This is defined as the melting point of solid. The line now goes from A to B. In going from A to B, heat is being absorbed by the solid, but the temperature remains constant. Under these conditions, the solid and liquid are in equilibrium. The molecules in the solid overcome the attractive forces by absorbing heat. The kinetic energy of the liquid molecules increases as more heat is absorbed. This results in an increase in temperature, and the curve goes from B to C. At point C, the liquid begins to convert to vapor. This is defined as the boiling point of the liquid. The liquid molecules absorb heat, and the temperature does not change. Under these conditions, the liquid and vapor are in equilibrium. All the liquid is converted to vapor at point D. After point D, the absorption of heat simply increases the temperature of the vapor.
Right. One important thing you need to remember here is the change of state. When there is change of states at this point A to B and C to D, the temperature is always constant. All right, no change in temperature. If you look at that, the temperature here is flat. So at any point when there is a change of state, the temperature is always constant.
Delta H subscript FUS is defined as the heat of fusion. The molar heat of fusion is the amount of heat required to melt 1 mole of a solid. Delta H subscript VAP is defined as the heat of vaporization. The molar heat of vaporization is the amount of heat required to vaporize 1 mole of a liquid. The numerical values of delta H fusion are small compared to delta H vaporization.
There are some calculations on this table, on this graph. When we get there, we're going to do more practice on the calculations. But remember, when there is a change of state, the temperature is always constant.
Certain solids evaporate and therefore have vapor pressure. A process in which the solid goes directly into the vapor phase is called sublimation. A process in which the vapor goes directly into the solid phase is called deposition. At a certain temperature and pressure, the solid and vapor are in equilibrium. This is expressed as a graph depicting the overall relationships among the solid, liquid, and vapor phases is called the phase diagram. The phase diagram of H2O is, this is a plot of pressure versus temperature. The phase diagram is divided into 3 regions: solid, liquid, vapor. Each region represents a pure phase. The line separating any 2 phases indicates conditions in which these 2 phases coexist in equilibrium. The point at which all 3 curves meet is called the triple point. Triple point is defined as the point at which all 3 phases can coexist in equilibrium with one another. For H2O, the temperature is 0.01 degrees centigrade, and the pressure is 0.006 atmospheres. In general, phase diagrams predict the changes in the melting and the boiling points as a result of changes in pressure. The normal melting point of H2O is 0 degrees centigrade at 1 atmosphere. The normal boiling point of H2O is 100 degrees centigrade at 1 atmosphere. However, if the pressure were greater than 1 atmosphere, there would be a decrease in the melting point and increase in the boiling point of H2O. Conversely, a decrease in pressure will lower the boiling point and increase the melting point.
So this is where you have to remember that water can boil at different temperature under different pressure. Okay, and that is why when you are at the top of the mountain, the water boils faster than when you are at the lower, because probably the pressure in the higher mountain is lower. So a decrease in pressure will lower the boiling point. So when you have a low pressure, you have a low boiling point. That means the water boils faster. Instead of boiling at 100, the water can boil at maybe 90 or 80 or 85 or 80 or 75 or something like that. All right.
The phase diagram of CO2 is, the phase diagram is divided into 3 regions: solid, liquid, and vapor. The phase diagram is very similar to H2O. The triple point of CO2 is at 5.2 atmospheres and minus 57 degrees centigrade. This is the reason why solid CO2 sublimes at 1 atmosphere. In fact, solid CO2 is called dry ice. The reason it is called dry ice is because it looks like ice but does not melt.
I want you to remember all these facts for AP exams, because these are the simple questions they can ask you and just give you simple answers, which doesn't require you to do any calculation. All right? All right, we do some practice here. Select the chemical species with the highest boiling points. That's question 1. Question 2, select the molecule with the highest boiling points. Remember, you can pause the video to give you more time, but try to work as fast as you can. Which among these substances exhibits the highest boiling points? Which of these substances exhibits the highest boiling points? Number 4, what causes oxygen to have a higher boiling point than nitrogen? Number 5, number 6, number 7, number 8, nine, and 10. All right, these are the 10 questions for practice. I'm going to get back to you in class on these questions. Watch out for the next video. Thank you.